In this class, let's talk about electronic drives for electrical machines for industrial applications. Before we continue, remember to subscribe in our channel, like the video and active the notifications, to help us grow in the platform. Electromechanical drive systems can utilize DC machines based on technical requirements and intended uses. Typically, the power source and the power processing unit, PPU, are viewed as a single component within the electromechanical drive system. In this setup, the PPU delivers electronic control, supplying the DC motor with the necessary DC voltage and current. This supply is regulated through converter circuits, which are classified into switched-mode converters and thyristor converters, both controlled by the network. Additionally, a DC motor can function using either permanent magnets in the stator or field windings. To vary the rotational speed of DC motors, a variable power supply is required, as the speed can be adjusted by changing the armature voltage or field current. Energy conversion and use of thyristors. A variety of circuits are employed to transform or regulate the electrical energy supplied to equipment. This regulation can be achieved through phase control of thyristors. These components, known as silicon-controlled rectifiers, SCRs, periodically control the flow of energy in the circuit, enabling controlled conduction and non-conduction. This method allows them to manage the output voltage, frequency, or both parameters provided by the circuit. The variable DC voltage needed to control the speed of a DC motor can be obtained using a line-commutated converter with phase control. To better understand the relationship between electronic drives and energy conversion using SCRs, refer to the energy conversion diagram shown in the figure. The arrows in the diagram indicate the flow of energy and, according to the legend, show the established relationship for the circuit and the circulation of electrical energy. Rectification involves a phase-controlled converter, specifically a line-commutated rectifier. Phase control by the thyristor, using a control voltage, enables a variable DC voltage at the output of the circuit to power the DC motor. Types of thyristor rectifiers. Thyristor rectifier circuits, also known as controlled rectifiers, are one of the primary applications of this type of device. These circuits are also referred to as static converters. They have various industrial applications, including the electronic control of a DC motor, and can be specifically divided into single-phase and three-phase circuits, depending on the power capacity delivered and the power supply network. Additionally, it's recognized that a rectifier operates across 4 quadrants of operation. It's crucial to note that in the first quadrant, the motor accelerates or maintains its speed in the forward direction. In the second quadrant, the motor brakes in the forward direction. Consequently, in the remaining quadrants, third and fourth, similar relationships apply as in the first and second quadrants, respectively, but in the reverse direction. In this scenario, the motor is powered by a single-phase semi-controlled rectifier using diodes, and the DC motor can be approximated by the presented circuit. When operational, the load behaves similarly to driving an RL load, supplemented by a DC voltage source. The inductance in this setup represents the armature reactance, and the resistance RA accounts for the armature resistance effects, along with incorporating the DC voltage to model the counter-electromotive force, back EMF, of the armature. VE denotes the input AC voltage, and VS is the supplied output voltage. In this type of circuit, the operation in terms of voltage variation is as follows: when the voltage EG, which can be interpreted as the back EMF of the motor, is sufficiently high, it prevents current flow, causing the thyristors to switch off during a single half-cycle of the AC supply. In this scenario, with no current flowing, the output voltage provided to power the motor will equal the armature voltage. Therefore, it becomes evident that the output voltage matches the rectified input voltage only when the thyristors are conducting and switching appropriately. If the current is discontinuous, for the thyristors to activate correctly, the input voltage must surpass the counter-electromotive force, back EMF, meaning it must exceed EG. This ensures that the thyristors are forward biased. As the motor accelerates, the armature voltage rises, and there is also a minimum firing angle required for the thyristors to conduct and control the motor's operation effectively. Additionally, another option is the utilization of a single-phase controlled rectifier, where only thyristors are employed in the circuit. Now, consider the application of a three-phase motor. In this scenario, electronic control can be achieved using either a three-phase semi-controlled circuit or a three-phase controlled rectifier, employing only thyristors. An example of such a three-phase circuit used for control is illustrated in the figure. This type of circuit, known as a Greets bridge, is essentially a combination of 2 three-phase midpoint rectifiers. As a result, it can deliver a voltage signal with reduced ripple amplitude, suitable for various types of loads. Its operation involves simultaneous conduction in each pair of thyristors, with commutation occurring at each phase transition. Consequently, the voltage across the load will have a frequency 6 times higher than that of the power supply network. Thyristor rectifiers and operating quadrants. Consider an electronic drive system with a DC motor and a thyristor rectifier circuit. Analyze the system to determine the relationships for motor rotational speed, armature voltage, voltage supplied to the motor, generated torque, motor power, armature current. Initially, the motor is at a standstill. When the system is turned on, the rectifier supplies voltage to the motor, which begins to accelerate until it reaches the desired speed. See the forward operation of the motor in the first quadrant. During the startup interval, the motor's speed increases due to acceleration, inducing a counter-electromotive force, CMF, in the armature. This induced force causes the circulation of current, allowing the motor to overcome the resistive torque and start operating. Since the induced voltage varies with speed and a similar relationship exists for the rectifier voltage, the following curves for these parameters over the operating time are valid, considering a startup time Tp until the motor reaches the desired speed. During startup, the produced torque depends on overcoming inertia. Once this is achieved, a specific torque value is maintained to sustain the motor's given rotation speed. The current over the operating time can be derived from the torque graph. During startup, the motor requires higher current to provide sufficient torque for acceleration. Afterward, a specific current value is maintained to sustain the desired speed. Finally, the motor power is directly related to the torque, the voltage supplied to the motor, and the speed. The maximum power occurs at maximum speed, and thereafter, the power remains constant at the value necessary to maintain the desired speed. Understanding the DC motor drive using a thyristor rectifier during forward acceleration. Let's consider the braking process. This can occur in two main ways, dynamic or regenerative braking. In regenerative braking, power is returned, and the motor operates similarly to a generator. The armature current flows from the motor to the grid. To achieve this, the armature poles must be reversed, as the thyristors conduct in only one direction. Dual converters are thus used, capable of functioning during both acceleration and braking, covering all four quadrants of electronic drive. Before delving into duality, consider the following examples. To establish electronic control for a DC motor that can accelerate and brake in the forward direction, the electronic circuit must allow for positive current and deliver both positive and negative voltage to the motor. This enables the motor to operate in the first and fourth quadrants of operation, as illustrated by the following rectifier configuration. On the other hand, when the converter operates with negative current and supplies both positive and negative voltage, it will function in the second and third quadrants. The following rectifier is an example of this configuration. 3-pulse dual circuit. In the previous circuits, Vs is the output voltage, alpha P is the firing angle for positive conduction, alpha N is the firing angle for negative conduction, Vp represents the positive voltage, and Vn is the negative voltage supplied to the load. Consequently, a circuit that can operate with both positive and negative current, as well as supply voltage of both polarities, is known as a dual converter. The equivalent circuit for this type of converter is similar to those seen in previous examples. Refer to the circuit in figure, which presents the equivalent dual converter for the 3-pulse circuit shown in the last figure. This diagram aids in understanding the operation of the dual converter. 6-pulse dual circuit. Finally, there is the 6-pulse dual converter, one of the most commonly used options in industrial applications. It provides voltage and current with fewer harmonics. This circuit is shown in figure. See you in the next class of electronic drives for electrical machines for industrial applications. Bye-bye.